Hi everyone. This is our first of our reviews. This is of first order equations. And so in general, a first order equation looks like something like this. Y prime is a function of x and y. This function could be very wild, but there's no prime in there. That's the main thing. No derivatives, only x and y's. Okay? So we have seen several techniques. And so now the challenge is a little bit for the final is, well, when we did each of these techniques, I told you which type of the first order we are dealing with, but now you have to recognize these types, and that's not always easy. And so you also have to then know what to do in case you find certain types. So I'll make a little bit of a flow chart here, so to see a little bit what we are in which steps you should use for this. So let me make it a little bit bigger here. Okay. So I'll make some boxes here of all different types. So the first type is it linear? That's the first thing we should ask. Okay, is it linear? And so linear means that it is of the form y prime. So okay, this is the form that we say how a first order equation looks like, but it doesn't always come in that form to us. And sometimes it's easier to put to present an equation in a different form, but you can better see what makes it of a particular type. So in the linear case, we would write it this way. Okay, so the pxy would be really, this pxy would really be if you bring this to the other side. But it's much easier to see that this is linear. Let's point out what is linear here means that there's only a single y here, and the rest is all functions depending on x. Okay, if that's the case, so there are two things, right? Is it yes or no? So let's put the yes here. If it's so, then what we need to next find out is basically, is it homogeneous or non-homogeneous? Okay, but let's put it all together, and you say, the first thing you do is the complementary homogeneous. Of course, if it's homogeneous, then it's just the thing itself. The complementary homogeneous, which is y prime plus pxy equals 0. So the forcing function, we call this f, the forcing function is 0. And in that case, what do? Well, we just integrate both sides. This is actually something which we have seen is we have separated variables, or you can make it separate variables. I will discuss that in more generality over there. But this case is rather easy. So what do you do then once you have that? So you find the general homogeneous solution, YH, I'm going to call it YH for now. The textbook doesn't talk about general homogeneous solution in first order, but in second order we do. So I think it's better just to do both cases in the same way. And this will depend, so it's important to know, this will depend on a constant, an integration constant. Okay, and so then the next step is to find a particular solution of the form y equals uyh. Why this yh is one of those that you have found there, but you can choose the constant however you want. Let me not do the little details here, but just give the big flavor of it. So that's, so in a yes of linear, we are okay. So let's make this in green. Okay, so if it's red, so this is no. What do we do then? So the next thing I think one should look at is whether it can be separated or not. Is it separated variables or not? So is it separated variables? Question mark. And what does that mean? In that case, is it separated variables? Then it's of the form qy y prime. So let me perhaps put a line here that we don't get, this is nothing to do with it anymore. So this is this box here. on. Qy prime equals, so this is the, yeah, okay, it's not, that's okay, Qy prime is equal Px. So that's the separated variables. Now, it might be a little bit, I'll give examples later, and then we will go through this if you use a flow chart. But you have to be a little careful. It doesn't mean that you can put all y's on one side and all x's on the other side. That's not enough. What you have to do is there has to be a single y prime, and then in front of that is a function that only depends on y. Okay, that's different. You'll see. You'll see what I mean with that. So if we are in this separated variable case, what we then do is, well, we just integrate both sides. Okay, so we just, if so, yes, we just integrate. So in some sense, this is an easy case, and this is exactly what I was pointing out here. If you're in a homogeneous, if you solve a linear homogeneous, that is a separated variables case. That's a special case, and that's why it's easy. Now, what you try to do is you try to find an explicit equation. Also, when you solve separated variable equations, you solve it at once. There's no homogeneous or anything like that. You solve it. You have always, of course, integration constant. Okay. So what if this is not the case? So again, suppose we are no. What is the next thing we'll do? Well, perhaps it's not separated, but perhaps I can transform it into separated variables. Can be transformed to separated variables. This is sometimes also called separable, but okay, let's not give a name to it. So if this is yes, well, the question is more, you have to actually, we have seen two cases, okay? So perhaps I should keep them orange because they are not really, so there are two cases. So one case is what we call the Bernoulli. And so how do these look like? Well, they look a little bit like linear, except that we have an extra power of y, which could be any power. It doesn't have to be an integral power. It could be a negative power. It could be a fractional power. Okay. If that's the case, what do we do in the Bernoulli case? Well, there's two steps. So again, let's say yes. So if this is, well, I guess the flow chart would be here, right? So if this is yes, what do we do? Well, we look again at the, I'm going to put it between quotes because this is not a linear, but I'm going to do the complementary homogeneous. Let's give that the same name because it's the same guy. It's y prime plus px y equals 0. So we solve that, separating variables, because that's what it is, right? And we find a homogeneous solution. Here you can take 1 because we're going to find the general solution by our method. And then the next step you do, so that's the first step. The second step is a variation of parameters. Y is u times this homogeneous one. So this is the variation of parameters, which was also the same here. I should perhaps have mentioned that here, that is variation of parameters, right? So in some sense, although it's not linear, we do exactly what we do in linear case, right? If you look at it, it's exactly the same thing, except be careful, we cannot put it together anymore, right? So here, so this is perhaps a little bit, it doesn't really matter. You can find here the general particular solution, and that will then give you the general solution. Or you can find a particular solution and add it to the homogeneous one to get the total solution. So that's what I should have said here. So this is yp. And then there's one more step here. Perhaps I should have said that is the general solution is the particular plus the general homogeneous. Okay. Now in this case, we don't put this together because this is not really the homogeneous part of this one because it's not a linear one. You cannot talk about homogeneous if it's not linear. So what we do is really look for a general y here with an integration constant. Okay, and this one we can take without integration constant. Little details. There's not so. What's the other option is that it is of the form. So this is what they call homogeneous, but let me not even fill in the box here. This is of the form y prime is a function in y over x. Okay, so this is called in the textbook homogeneous, but it means something else. It means not. It's very unfortunate that the word homogeneous is used in two different ways, and so let's not give that name to not get or confuse ourselves. So I'm just going to say of the form y over x. And then what we do is we just do y equals ux, and then again variation of parameters, and we solve this the problem in general again. So okay, let me say this. So general constant. So here also we will have a general constant, whereas here we normally don't do a general constant in this case. Sorry, let me get this line a little bit out of the way. So this way, right? In this case. Sorry, it's this one here. So the one here, we do it a little bit differently because we follow more the structure that we would do in second order. It doesn't matter. You can do either one, and I think the textbook does it the other way. But okay, so these are the two that can be transformed. We have not seen other ones. There are other, but we haven't seen other ones. So let's see what happens if that's not even the case. No. So then we have only one more left, and that is it exact? And so those have a very special form. They look like this: mxy dy plus nxy dx equals 0. So here we, instead of y prime, we're writing dy dx and then clear the denominator, so to speak, because that is much more telling than if. So exact means, so let me pose it as a question. So what is the question? Is what we have to do, you take the partial derivative of m with respect to y, is that the same as the partial derivative of n with respect to x? And I say it this way, and it's the other way around, right? So it's the partial derivative with respect to x is that equal to the partial derivative of n with respect to y. So it has to be the other variable, okay? If it's yes, so yes. If it's no, then it's like hopeless, or look again, because it must have been something else. Okay. Yes. What we do then? Well, then we find f, which is the integral of this mdx with respect to y. I'm now thinking if I put my m and n's in a different order. I should let me try to use the same m and n's here, so that might be a little bit. Yeah, okay, I see what I saw. So okay, what I wrote is all correct, but let me write it more like the textbook writes it, because that's perhaps less confusing. So they use m for the one in front of dx, and n for the one in front of dy, and then it is my equal to nx. It's the other variable again. Okay, so yes, if yes, then what we do, well, we know that an exact what that means. Yeah, this means, so let me say it in this way, it follows from that m is actually the partial derivative of a function f, and n with respect to x, and n is the partial derivative of function y, and it's the function f that we find. So we want to find f such that these two things are true, and then the solution, and this is a little bit something that you have to keep in mind. The solution is not f, the solution is f equals c, because f is just a function. F is going to be a function in x and y. So if you just give a function x and y, that is not a function, right? That's just an expression in x and y. So this f is just an expression in x and y. So I said misspoke. I said f is a function. No, I should say f is an expression in x and y. And if you take the partial with respect to x, you get m. And if you get the partial with respect to y, you get n. Why is that? Because this is true. If this is true, right? So I'm in the yes case now. So so let me not make it anymore as a question, but say yes, it is true. So I'll say yes here. So we're in this case. Okay, so if we're in this case, then we know such an f exists, and this expression f is then gives the solution by putting f equal to a constant. Okay, and how do we find these m and x? By something what we call partial integration. I will do an example. I'm not going to work out the details now. I'm not going to spell them out. I'll show it on an example. So that's the chart. That is what we do with first order equations. So let me now do this in practice here, and I'll write down a couple of examples that I had. I'll write them all in this form, which might be misleading, okay? But that's the reason I'm doing it. So here's one: y prime is equal to 3y squared minus 6x squared over x squared. Let's call that 1. Number 2 is y prime is equal to 3x squared y squared plus 3x squared. Number 3 is y prime is equal to y plus xy squared. And number 4 is what is, sorry, I forgot about one. Sorry, y prime is equal to x to the 4th minus 3x squared y, and the 5th one is y prime is equal to minus 2x plus y divided by 3y squared plus x. Okay, I kept them in some sense simple, but okay. Since I all write them in the same way, it's not easy to recognize what they are, right? So let's go through the chart here. And therefore, yeah, okay, let's do this. The first one. Okay. Let's is this linear? Now remember, linear is very, very special. It means there is only one y prime and nothing, and one y, and that's it. Okay? That's clearly not the case here. We have a y prime, we have a y square, but there is also here there's a y square, right? So this square already rules out linear. So let's say that. Let's make it red. This one says not linear. Okay. So what's the next thing then? Can we separate the variables? Right? We are jumping now. So no. Can we separate the variables? In other words, can we write it this way? So how do we know that? Well, you can only know that by trying. Okay. So. But you can tell already this is going to be difficult, right? Because for one thing, okay, you can bring the x squared to there. And what then? Now remember, we have to bring this, the expression in y, together with y prime, and all the x's together. And once you start putting this to the other side, you see there's no way I can do that. So this is not, so I can not separate the variables. Well, the next thing is then perhaps, can I transform it into separated variables? Okay, so I'm now looking at this question, and that means, is it of either two forms? Is it Bernoulli? Then a Bernoulli must have a y and a y and a y, another y, another power of y. But there's only one y squared, so I don't even have y here. So it's not Bernoulli. Okay, again, not Bernoulli because there is no y. Okay, it's not Bernoulli. What about the other form? Can it be written as a function in y over x? Now that requires us some manipulations. And so we have to see, well, perhaps, let me go with black now, because I'm going to solve it now. How do I know can be y and x? Well, it's written as a quotient, but perhaps I should then carry out this division. And then now we see it, right? If I divide each of the two terms, then I get 3y over x square minus 6. That is the result of dividing. If you do this right away, then it might not be necessary to do this. So don't start doing this until you're convinced, okay, this is what I should do. So yes. So number one, we have recognized as it's of the form 3 y over x squared minus 6. And then what we need to do is variation by parameters y is ux. So y is ux. So perhaps I should box those guys to remind us what it is that we will do, right? So these are then the substitutions we want to do. So I'll do it here, box it. Because we have to go back to this, right? To never forget that you have to go back to the y. Okay, so what is that we do? We take y prime, product rule, u prime x plus u, derivative of x is 1, and plug it in. So we get u prime x plus u is equal to 3 times, no, y over x is u, 3u squared minus 6. Okay, so that is u prime x is equal to 3u squared minus u minus 6. Okay, okay. I think I might have put here the wrong yeah, I sorry, I copied this wrong. I just want to change the numbers because otherwise it's going to be ugly. Sorry. So I'm sorry. This should have been originally had this, but this should be a 2 here. It doesn't change anything here, right? So this should have been a 1, and this should be a 2. Otherwise, I don't want to get two ugly numbers and you start yelling and screaming. Say, well, this is. So this was what do we say here? This was no, what was it? A 2. So this was u squared minus 2. So this is that. Okay. So we know this has to be right. I should say this, right? So where either case when we do this here or this one, it's a variation of parameters, but it goes back. The whole point is that we will go back. So I should have perhaps put this here. We will loop back to this case. Oh, let me do it in orange here. So we will loop back to that case, right? Right. So well, okay. So we loop back to that case. That's the whole point. So this should now be in U as separated variables. Okay. So that is actually true, because if I now divide both sides, bring the x to the one side, that becomes 1 over x, and then the u prime becomes u squared minus u minus 2. I have now, this is separated variables in U. Okay. So what we need to do then is, let's look at what we need to do. If the separate variables, we just integrate. Okay, we just integrate it. I prefer to write it always this way. I hope you remember that we're using that u prime is du dx, right? And then kind of multiply the dx to the other side. Okay, so we have to derive this, and we have to derive this. This one is easy. That is ln of x plus a constant. Let's in this case we have to keep the constant. What here? That's a partial fraction. So we have to do the partial fraction of 1 over u squared minus u minus 2. Well, the first thing is, can we factor this? So two numbers that multiply to -2 and add up to -1, I think that is -2 and plus 1, right? -2, yes. So we know it's of the form a over u plus 1 plus b over u minus 2. And now we are at the end of the course. The course we have learned a lot of techniques, so we know Heaviside can do this very quickly for us. So we look at 1 over u plus 1, u minus 2. So that is a would be on top of u plus 1. So I'm going to put in u is -1. U is not a variable, not s, that we have been doing recently. We scratch out this u plus 1, and we plug in, and we get -1 over 3. Okay? And what about b? So b is 1 over u plus 1, u minus 2. Now we plug in u is 2, and we sketch this one out, and I get 1 over 3. Okay, so we get this. This is minus 1/3 u plus 1 plus 1/3 u minus 2. And so if I antiderive this, this will be the ln is minus 1/3 ln u plus 1 plus 1/3 ln u minus 2. Okay, so I'm sorry, I'm a little bit. So these are two equal now. So this is where we are. And then remember what we said then, if you try to make an explicit equation, because at this point we do have an implicit equation. Well, not yet. No. Okay, sorry. We have to solve for y. So I should perhaps make this clear here. Integrate. We know that we're looping back. When we're doing this here, variation of parameters, we have to get back y. Okay, and we are doing a separated variables, but in u. It's a separated variables in the variable u, but we have to go back to y. So we have to solve for u in this case. So here we have to do explicit, because otherwise we cannot write down what y is. So let's do that. So how do we do that? Well, combining ln's. First of all, we bring the 1/3 over. So this is ln of u plus 1 to the power minus 1/3 plus ln u minus 2 to the power 1/3, and that is equal to the ln of x plus c. And then to combine the ln's, that's the product. So this is the ln of u to the u minus 2 to the power 1/3 over u plus 1 to the power 1/3. Because I'm thinking of negative exponent is actually in the denominator, okay? And so that's what this is. And this is ln x plus c. Now we take the x, we exponentiate this. And so we get that u minus 2 over u plus 1 to the power 1/3, let's write this now all in one single power, right, is equal to e ln x plus c, which is just e c times e ln x, which is just x. And then we replace this constant by a new constant, let's call it ax. So are we there? No. But we can now, what do we do now? We have a 1/3, that's a cube root. So to cancel that, we take the third power. So we get that u minus 2 over u plus 1 is a cube x cube. But there's no reason to write a cube. Okay, so I'm going to rename my constant again, and let's call it c again. I know it's a different c. So this is a rename x cube. Because you might say, but Professor, we're not supposed to do that, to use the same name for different things. Unless that thing stands for any possible thing, for any possible value, then it doesn't matter really. If it's any possible value, then we can write it this way. We can rename it, okay? Are we done? Not really, because we still have to solve. So here's u minus 2 is equal to cx cube u plus 1. We expand, that is cx cube u plus cx cube. And then bring the u terms to one side. U minus cx cube u equals cx cube plus 2. So now we can solve for u. That is u1 minus cx cube equals cx cube plus 2. So u is equal to cx cube plus 2 over 1 minus cx cube. And so y is, remember, now we go back to our pink thing here. Y is that times x. So it is x times cx cube plus 2 over 1 minus cx cube. And that's our solution. And you see, it depends on this constant c. And then the one thing I did not address here, because I hope that is now clear how to do that, is finding this constant using initial conditions. So I'm not going to talk about that, because that's a general technique that you should have now understood very well. Okay, that's the first one. Let's look at the second one. The second one, okay, so let's go to our thing again. Is this linear? Well, no, this 2 again tells us not linear. So it's not linear. So I can rule that out. What else? So separated variables. Not really, right? Because there's no way I can get the y square and the y prime together and nothing else, right? The x squares are in the middle there. No way that this works. Okay, what else can I do? So it's not linear. It's not well, but perhaps you should try a little bit more. So let's see, is this true what I said, that you cannot do this? So that's why it looks like you cannot, right? In the first you said, no, it doesn't work. But that's the problem. You have to play a little bit with this thing. So for instance, I noticed that there's a 3x squared here. So I can actually write this y prime is 3x squared, and then I've left y squared plus 1. And once I write it this way, the heavens open up and we see, yeah, we can separate because it is y prime over y squared plus 1 equals 3x squared. So it might be something doesn't immediately look like, and you now you might start doubting perhaps this was also possible then, but when you play with it you see it's not. Okay, so it's sometimes hard to recognize what form it is. So okay, we now know that 2 is separated variables, so this is separated variables. And so what we need to do in the separated variables, just integrate. That's what we did. We have done this already, so that's why this will be hopefully a little bit quick. So number 2, so we had y prime over y squared plus 1 is equal to, where is my guy? 3x squared, okay? And let's already write it with dy's, is 3x squared dx. That makes it even easier. Okay, so we just antiderive. This is arctangent. It's one of these special functions, right? Arctangent. And that is equal to x cubed plus a constant. We need a constant. I'm going to call it d now because I know we're going to change it perhaps. Well, actually in this case I'm not going to change it, so I'm going to keep it c. This is our solution. Okay, we are done in some sense because we have an explicit solution. Why were we not done here? Why could we not stop here? Because we have an explicit solution. Sorry, I didn't want to. We have an explicit solution in U, but we need an explicit solution sorry, we have an implicit solution in U, but that doesn't give us an implicit solution in Y. Now, granted, what you could do, if you're really lazy, or sometimes it's not, you have no other choice, is replace U by Y over X, because that's what it is, right? U is Y over X. So if you replace here Y over X and Y over X, you would have indeed an implicit equation. But try to always solve it. And again, here we can solve, because we can take the arctangent is the inverse of tangent, so tangents will cancel it. So Y is equal to the tangent of x cubed plus c. And that is our solution. There it is. All right, what is number 3? Let's look at the third one. Y prime is y plus xy squared. This looks linear? No, because of the y square, it's not linear. So this again tells me it's not linear. So if it's not linear, what's the next one? Can we separate the variables? That was very successful last time, so let's try to see what you can factor out the y, but then there's still one extra y that doesn't go, right? Here, playing with the y and factoring is not going to work. Okay, so trust me. Okay, that is something you have to try a little bit to see, and sometimes, by the way, it is very well possible that there are different ways of solving the same equation, right? It's not true that it's only one of the possible cases that can solve it, but in this case, it's not separable variables. Okay, so then the next thing that we should do is perhaps can we separate, can we transform it? And so we have to ask, is it a Bernoulli or is it of this form? Now remember, this is how Bernoulli looks like, and once you look at this, you see, okay, this y that we would normally write the y to the other side, so it looks like a Bernoulli. So this is a Bernoulli, and so we know what to do now. Okay, let's solve this now. So for the Bernoulli, so this is 3. So this is y prime, and I'm going to write it now already in, bring the y to this one side. So y prime minus y equals xy squared. So notice this so I'll write down one more time how the form of a Bernoulli is, right? This is how the form of the Bernoulli is. is, so r is 2 here, f of x is x, and px is just minus 1. But it is of that form. So what we need to do, well, let's go see what they tell us. In the Bernoulli, you look at this so-called complementary homogeneous. Technically, it's, I don't know what to call it that way or not, but so what we the first step we have to do, so the first step is we solve this equation. Now we know that this is always a separated variable, so this is y prime equals y. Is that separated, the variables? No, the y should be on the y prime side. So y prime over y is 1, or perhaps more telling, dy over y is dx. So I prefer this way because now it's easier to see that you have to integrate, and with that on the left you integrate with y, the right you integrate with x. So this is ln y is equal to x plus a constant, let's call it d. So taking the exponential, this y is equal to e to the x plus d, which is e to the d times e to the x, which we call cex. Okay. And what is the next thing then you do? In the Bernoulli, where is my chart? Bernoulli. I'm using the general one here. I'm going to find the general one by variation of parameters to take one of these homogeneous. So I can here take, you can take C to be 1. So not 0, because then you don't get y is equal to uex, and we do variation by parameters. So let's rebox this again, because we're going to have to come back to this guy. Okay, so this means that y prime is equal to u prime ex plus uex. We plug this in an equation, the equation up there, that is u prime ex plus uex minus y, which is uex, is equal to x y squared, but y is u squared e 2x, right? Don't forget there's a y here too that has to be substituted, right? Now what we need is, one thing has to happen is this has to be separated variables. We have to be able to separate variables, and this means always some cancellations. And so this is the cancellation that we were expecting, because now we see that we can separate the variables by the right division. So bring the u squared to this side, and then the ex to the other side, so I get e 2x divided by ex, that is ex. I hope that's clear that we subtract exponents here, okay? And so, or perhaps better to write it as this way, u squared du, u to the minus 2 du, equals x ex dx, and we have to end the derive. Okay, this is the power rule, minus add 1 to the exponent divided by the exponent, and that is equal to, and this is integration by parts, right? So I'm going to do it a little bit on the side here. Unfortunately, there's a u that I have to use, but that's okay. It's temporary. The u stays in the box. So u is x, dv is ex dx, so du is dx, and v is therefore ex. So we know that this integral is equal to uv minus integral v du, which is x ex minus integral ex dx. Okay, so we find that this is equal to, I can write it now here, x ex minus ex. Okay, oh, well, I should have written it here. Put it here. X ex minus ex plus a constant. We're going to do here the general constant. Okay. And we have to solve again for y. So you could simplify this a little bit. I don't think it makes much of a difference. What we need to do is take reciprocals, right? And then, so 1 over u, but this is 1 over u, so I take the reciprocal. This means that u is minus 1, the minus sign I'll bring to this side, x minus 1 ex plus a constant c. So this is y. Are we done? No, because this is what the solution is. So y is equal to that guy, so minus ex over x minus 1 ex plus c. Okay, so that is our solution. Now, it is not uncommon to divide everything by ex, because it makes the expression a little bit simpler. This is the same thing. If I divide every term by ex, of course this becomes a 1. This cancels, and this becomes c over ex is c to the minus ex. So this is also a way that you can write the same function. It looks a bit different, but it is the same. Okay. All right, that number 3. Let's go number 4. Y prime is x to the 4th minus 3x squared y. Oh, professor. Oh, this is linear. This is linear. Look no further. Because if it's linear, it could be something else, but if it's linear, I know what to do. I don't want to think more. Okay. So let's write it in the linear form. So that would be I'm going to copy this because if I have to go back so many times, I'm going to get. So let me write this as y prime plus 3x squared y equals x to the 4th. Okay, so this is now, so we know it's linear, so we have the step 1 is the complementary homogeneous. That is y prime plus 3x squared y equals 0. We know this is a separating of the variables. So we separate the variables this way, that is y prime over y is minus 3x squared, or perhaps dy over y is equal to minus 3x squared dx. Okay, so if I enter derive, this is the ln of y is equal to minus x cubed plus a constant. But yes, the constant we need for the general case, we need to take the exponentiation here. We exponentiate, so y is equal to e to the minus x cubed plus c, that is, or plus d, let's call it d now, because I'm going to write this as e minus x cubed ed, and then I'm going to make that into a c, right? C e minus x cubed. So this is my general homogeneous solution. What do we do next? Then we go step 2. If you let's look what the chart tells us to do, right? We then look for a particular solution of this form by variation of parameters. A technique that is very many times, many cases, that's what you do, right? So y is equal to u e to the minus x cubed. That means that y prime is equal to u prime e to the minus x cubed plus, now be careful, there's a chain rule going on here. The derivative of minus x cubed is minus 3x squared. Then u, that's just the first factor. And then we have this guy. Okay, and that we plug into what? Well, into the actual equation. So the one up here. So okay, I can copy it again, I guess, right? Because I have it. So that would give me u prime e to the minus x cubed minus 3x squared u e to the minus x cubed is equal to x to the 4th. Yeah, right. So this one had gone to the other side. Is equal to x to the 4th. That was it. What it was. And this is, well, okay. Sorry. This is y prime. X to the 4th and minus 3x squared. I have to still do this, right? And y is u e to the minus x cubed. Sorry, that's what I meant to say. Okay, we know that something has to cancel here because that's the variation of parameters technique tells us that we need to get rid of something, and this is the guy that we get rid of. Because what it will come down to is we should be able to solve for u prime. And in terms of x, so it reduces it to a integral, a real integral calc 2 problem. Okay, and that's what we get, right? We get u prime e to the minus x cubed is x to the 4th, and bring that ex cubed to the other side. U prime is equal to x to the 4th e to the x cubed. So u is equal to the integral of this thing. Now it looks hard, but it actually is not so bad. If I do the substitution, w equals x cubed, so dw is 3x. Oh no. Oh, this is a bad one. Oh, sorry, I must have copied this again wrong. Because this was supposed to be, I'm sorry. Yeah, I just copied these things very quickly, and I might have copied. So this in x to the 4th, I'm going to make this in x 2 here, okay? So far, nothing has really changed, right? I've not really done anything with this. So this should be a 2 here. So where would this come up again? Here again, and then here, right? X squared, x squared, x squared, x squared. So, sorry. So that's what it's supposed to be. So 3x squared dx. So this is equal to 1/3 EW dW, right? So okay, dW over 3 is equal to x squared dx, right? That's what we have. So this is the x squared dx. That's the W over 3, which the 1/3 took out already. Okay, so and that of course is just 1/3 EW, and therefore this is what are we looking for? This is homogeneous, so we look a particular solution, so we don't need to think of constants here. So I'm going to just write 1/3 e to the, and w was x cubed, right? Okay, so that is u. Now we have introduced u. Oh, I should have boxed it, right, to remind myself that it comes from something else. So we find that y is equal to 1/3 e to the x cubed times e to the minus x cubed. Well, that means y was just 1/3. Now that's a particular solution. Okay, 1/3. That we didn't think of it right away, but actually it turns out that that's a solution. Okay, and okay, so we put together the general solution. So this is a particular solution. Let me write it here to remind myself. So that is 1/3 plus the general homogeneous solution, what was c e to the minus x cubed. And so this is our y equals that thing, of course. Yeah, our how it looks like. All right. Okay. And then so what else do we have? That was, which one do you do now? 4 or 5? Okay, so at first you might say, oh, this might be Bernoulli because it's a y and y squared, but then you realize, no, there's no way that y, it's not, the y squared is not in the right position, right? In a Bernoulli, like here, we need something like that here, but here we have a denominator here. So next time with the quotient, well, perhaps we can write it in terms of y and x. So what you do is then divide everything by the highest power. So divide everything by x squared. Now that would be a 1 over x here, a y over x here, no. So it won't work, right? Because the degrees are not correct. So here, if I want to make this y over x, then I have to divide this by x squared. But then I get a 1 over x here, I get a 1 over x and y over, and 1 over x times y over x. So it doesn't work. It's not of that form either. Can I separate the variables? Again, you could multiply out and play with it, but you cannot separate the variables. So so it's not separated variables. Can I transform it? We already said it's not Bernoulli, it's not that. Sorry, I should have followed my chart here, but my point is none of these happen exact. So the only thing left is exact. Now it doesn't look at all in the form of an exact. So let me copy this now. And that means we first try to write it as an exact. Okay, so if we write it like an exact, remember an exact looks like m dx plus n dy equals 0 with m and n, such that m of my is n of x. Okay, so let's try to write it that way. So we multiply here. This becomes y prime equals minus 2x plus y. So perhaps I should bring this to the same side, right? Because look how it's written. Everything is written on one side. So if I do this, this comes a plus. So I'm going to be a little bit lazy here and put a plus here. Is 0. What about this dx and dy? Well, that is because y prime is dy dx. So we should write it in this form, even more telling then. So we should write 3x squared y squared x dy plus. And what happens to dx? Well, this whole thing is multiplied with dx, right? Think of this just as a fraction, and then that's what you have to do. Okay, so now at least we got it in the form. So if this is m, and then this is n, and what we have to calculate is my. What is my? The partial derivative. Oh shoot, I copied this. Jesus, people, I'm so sorry. I keep copying this thing wrong. It's the reciprocal fraction. Sorry. I apologize for this. So I wrote a fraction wrong. It's the fraction. It's the flipped over fraction. Yeah. Okay. Let me. Okay. It's the same problem, but let me do it over. Okay. Sorry. I'll write it up. What I meant to do is this one. Y prime is equal to minus 3y squared plus x over 2x plus y. So because, right, what was my here? Let's check. Why did I say, oh, it's wrong? Because what is my? The partial derivative. Oh, no. It is correct. Sorry. I'm so sorry, guys. I did, no, everything is correct. I got myself confused. Everything is correct. What I said is correct. It's just, I call this m and then n, and yeah, I don't know why the book writes it in this order. This is the more natural order if you work with these things. Okay, so I call this m, but it is actually the n. And I call this n, but it's actually the m. But that should not really matter. What you have to say is, what do you have to do? So is this exact? What I have to check is, well, this is a function of in front of dy, so I have to take the derivative with respect to the other variable. So m of x, that's what I need to calculate. Okay? So, okay. What I wrote down is correct here, but the m and n's are the opposite of what I have here. So that's why I was really confused. So it's better to know, but see, that's why formulas sometimes can be misleading rather than helpful. It's better to say, tell yourself, this is the technique. You look at what is in front of dy and you take a derivative with respect to x. What is that? Well, derivative of 3y squared, that's constant as far as x is concerned, that is 0, and the derivative of x is 1. So it's just 1. Okay. What is ny? So the derivative of 2x, as x is now between respect of y, so that is 0, and the derivative of y is 1. So yeah, they are saying equal, very simply equal. Then we know that this has to be f of y, and this is going to be an f of x. Now it's the same variable, okay? That is the f. And I can choose from which one I start. It doesn't matter here really much, but it looks the simplest to me is to start from this one. Okay, so let's start from this equation. So we have the partial derivative of x is 2x plus y. So let's find what f was. So what we're going to do now is what you have told you should not do in calculus is to take the antiderivative with y in there. But for us, y is now a constant. Okay, so this is the partial antiderivative with respect to x. Okay, so what does that mean? Well, the antiderivative of 2x, of course, that's x squared. There's no problem here. But what about this y here? Well, y is, as far as x is concerned, in this integration, a constant. So we get plus yx. Now, perhaps in the beginning, this was more confusing. But remember, in our convolution integrals, we had the same problem. We had a z and a t. And the t was a constant with respect to z. Okay, now, very important is that there is still something here, a constant, but it's not just a c, it's a constant that could depend on y, because y, as far as this integration is concerned, is a constant. So be careful that you don't write here just c, but it has to be phi of y, a function in terms of y, because we integrate with respect to x. If you do the other way around, it's the other way around, vice versa then, okay? What is then the next step that you do? So that was step, I don't know, this step, next step. You use this expression to calculate fy. So now you take the derivative with respect to y here, the partial derivative. X squared doesn't do anything. The partial derivative of yx, what is that? With respect to y. X is a constant, and the derivative of y is 1. Plus, well, that's now the phi prime, right? Because we don't know what phi is, we can only write the phi prime. What do we do with this? Well, we know that this is equal to this guy here. So we know that this fy is equal to 3y squared plus x. And if everything works out, then this should give me an equation only let me keep writing the y here. Because the x's have to cancel, which they do locally, right? So we have an x on this side and x on this side. So what we find is the equation 3y squared equals phi prime. So now we can antiderive. Phi is the antiderivative of 3y squared dy with respect to y, of course. That is y cubed. Should we put a constant here? No. We're looking for one single f, because now let's write down what we have. We found that f is the only thing that we didn't know of was this part, right? So we find this is x squared plus yx plus y cubed. So this is our f. Is that the solution? No. Remember, and go back all the way up here. In exact, this is the solution. The f is an expression in x and y, but as an expression, it's not an equation, so it doesn't define anything, right? It's just the expression f. You say, oh, f equals x squared plus yx plus y cubed is the equation. No, f is that thing. It doesn't give us anything. So the equation is, so solution x squared plus xy plus y cubed equals to c. This, of course, is implicit, and we could try to solve it explicitly, but in this case, this doesn't work well. It is sometimes possible, but with exact, often it's not really possible. And so we have to leave it that way. Alright, so I went over all the techniques of solving a first order equation. Now, of course, we also have applications of first order equation with our mechanics and so on, but I'm not going to review that. That is, for that you look at the reviews of the origin of the quizzes, particular quizzes. Okay, and so then we will deal with second order in the next reviews.